Hello, in today's video we're going to be looking at this question from Further Mathematics Paper 2 of the Littoral Mock 2020, and the question involves further applications of integration as well as curve sketching and inequalities. It says the arc of the curve with parametric equations x equals cos squared t and y equals 2 sin t for t lying between 0 and ln of 2 inclusive is rotated completely through 2 pi radians about the x-axis. Show that the surface area generated is pi over 3 p cubed minus 8, where p is a number to be determined. In the second part of the question, we have that sketch using the same axis the curves x squared equals y cubed and x squared plus y squared equals 16. Hence, find the solution set to the inequality x squared minus y cubed into x squared plus y squared minus 16 greater than or equal to 0. We'll start with the first part, which is asking for the surface area generated when the curve is rotated 2 pi radians about the x-axis in the interval 0 less than equal t less than equal ln of 2. The formula booklet provides the formula for the surface area in the case where the curve is given parametrically as integral from 0 to the upper limit of the interval, which is 2 of 2 pi y the square root of dx dt all squared plus dy dt all squared dt. And so we have the task of finding the expression for dx dt all squared as well as dy dt all squared. Now we'll begin with x, which has been given in the question as cos squared t, which I can also write as cos t all squared, so that dx dt using the power rule would be 2 cos t then times the differential of cos t, which is sin t, and from there dx dt all squared is what we require. That will be the square of 2 cos t sin t, 4 cos squared t sin squared t. Then we also have y equal 2 sin t, so that dy dt should be 2 cos t, and from there dy dt all squared should be equal to 4 cos squared t. In the formula then we have integral from 0 to ln of 2 pi y, and y is 2 sin t, then times the square root of dx dt all squared, which we had as 4 cos squared t sin squared t, 4 cos squared t sin squared t, plus dy dt all squared, which is 4 cos squared t, 4 cos squared t. This gives 2 pi times 2 will give 4 pi, so we can take it out of the integral sign. Then we have integral from 0 to ln of 2 of sin t, the root of, in the square root we have 4 cos squared t, that is common in all the terms, so we have 4 cos squared t into, we divide every term by the common factor of 4 cos squared t, so we get sin squared t plus 1, and that is with respect to t, so dt. This will be equal to 4 pi integral from 0 to ln of 2 sin t. The root of 4 cos squared t is 2 cos t, and then the root of sin squared t plus 1, which is cos squared t. Finally we get 2 times 4 pi, which is 8 pi integral from 0 to ln of 2 of sin t cos squared t dt, since the square root of cos squared t is cos t, which multiplies this other cos t to give cos squared t. Now the integral of sin t cos squared t can be obtained by recognition. Recall that d over dt of cos cube t should be equal to 3 cos squared t sin t. That implies that cos squared t sin t is equal to 1 all over 3 d over dt of cos cube t. And so the integral of cos squared t sin t dt should be equal to 1/3 cos cube t plus the constant of integration. Actually, the principle behind this method is the fact that differentiation and integration are opposite processes. If I differentiate the function on the left hand side to have the one on the right hand side, it means that if I integrate the one on the right hand side, I'll go back to the function on the left hand side. This is simply the principle which has been applied to get this integral. So we then have that the surface area would be equal to 8 pi into the integral of sin t cos squared t dt, which is 1/3 cos cube t, and we're taking from 0 to ln of 2. This gives 8 pi into 1 all over 3 cos ln of 2 all cube minus 1/3 cos 0 all cube. This will be equal to 8 pi all over 3. 1/3 is common in all the terms, so I factorize it, it becomes 8 pi over 3 into cos of ln 2 all cube. So I get half into e to the ln 2 plus e to the negative ln 2 all that cube minus cos 0 is 1, so 1 cube. 8 pi all over 3 into half into 2 plus half. E to the ln 2 is 2, e to the negative ln 2 is half. All that cube minus 1. 1 cube is 1. This gives 8 pi over 3 into half into 2 times 4 plus 1 is 5 all over 2. All that cube minus 1, and we get 8 pi all over 3 into 5 over 4 all cube minus 1. Now the question requires us to show that that surface area is pi over 3 into p cube minus 8, where p is a real number to be determined. So we get pi over 3, which is outside the bracket in the required proof, and then we multiply or expand 8 into the bracket so that we get 8 times 5 over 4 cube, and 8 is a 2 cube into 5 over 4 all that cube minus 1 times 8, which is 8, and finally we get pi over 3 into 2 into 5 over 4 all that cube minus 8. Finally we have pi over 3 into 5 over 2 all cube minus 8 as the required surface area in square units. So the area is this, and we can conclude then that P is 5 all over 2 as the question said. In the second part of the question, we are asked to sketch using the same axis the curves x squared equals y cubed and x squared plus y squared equals 16. Hence, find the solution set to the inequality x squared minus y cubed into x squared plus y squared minus 16 greater than or equal to 0. So in the second part of the equation, we have x squared equals y cubed and x squared plus y squared equals 16. So we are required to sketch these two curves on the same set of axes. So we'll begin with the vertical axis, the horizontal axis, we have the y-axis and the x-axis. The first curve is given by x squared equals y cubed, and this is a semi-cubical parabola with the higher degree cube being on y. So this is a cubical parabola whose axis is vertical. So we have this shape for it. If the higher degree of 3 was on x squared, the axis of the semi-cubical parabola would be horizontal. That means the x-axis. The other curve, x squared plus y squared equals 16, is a circle whose center is at the origin and with radius 4. So we can make the sketch of that circle, center at the origin and with radius 4. So the fact that the radius is 4 would be very important for us to indicate the boundaries of our region, especially as we are going to be determining the set of values of the inequality given for us to solve after the sketch. So this curve is that of x squared plus y squared equals 16, and this other one is that of x squared equals y cubed. So this is the sketch of the two curves on the same pair of axes. And now in the last part of the question, we are asked to use the sketch and determine the set of values of x for which x squared minus y cubed into x squared plus y squared minus 16 is greater than or equal to 0. To solve this inequality using the graph, we are going to start by shading so as to leave unshaded the region of the xy plane for which the inequality is satisfied. So the region where there are other pairs xy that will satisfy the inequality. So to begin, I would take a random point. Let us say that point where x is 2 and y is 0, which is in this region. So I will test for the sign of the inequality in this region. So once I determine it, it would serve as my reference, and I will then be able to determine what is happening in the other regions as far as the inequality is concerned. So I would simply determine the sign that the function x squared minus y cubed into x squared plus y squared minus 16 has in this region marked red. And to do that, I will use the point 2, 0. So this point is 2, 0, and it doesn't lie on any boundary of the curve, so it is good to go. So when I substitute 2, 0 in the function, I have 2 squared minus 0 cubed into 2 squared plus 0 squared minus 16, and I get 4 into 4 minus 16, which is negative 12, and that gives negative 48. So it shows that the function would always be negative in that region, but we are looking for the region where the function is either equal to 0 or positive. So that region, the solution set of the inequality cannot lie in that region. It's colored in red to indicate that the set of other pairs that will satisfy the inequality would not lie in this region. Now, the quick way, a trick that you will be using once you have shaded one of the regions in a question like this, would be that once a region bounded by the curve or the set of curves doesn't satisfy the inequality, then the next region immediately after it would satisfy. So this region becomes the region that will satisfy the inequality up to this boundary, and the next region also would be the region that will satisfy. So as you move from a region that does not satisfy, the next region must satisfy, and then the next region will not satisfy, and so on. So the regions keep alternating as you are moving from one region bounded by the curves to the next. So this next region will not also satisfy the inequality. So overall, we then have these two regions that have been ticked in red. Any other pair found in the two regions would belong to the solution set that satisfies the inequality. There are an infinite number of other pairs in these two regions that we have ticked that will satisfy the inequality. Okay, you can try. Take a point here like 0, 2, and you test it in the inequality, you see that it will satisfy. Take another point in this region like 5, 0, and substitute it in the inequality, you see that it will satisfy. So the conclusion will be that the solution set is the set of all ordered pairs, x, y in the unshaded region of the x, y plane. Thanks for watching, and if you are new to the channel, please consider subscribing and activating the notification bell so that anytime I post a new video, you will be able to get the notification and then watch.